Check.
All good. Right. I'm gonna introduce you, Vincent, and then I'll hand
Oh,
over. Um,
sounds
Hi everyone. Thank you so much for being here. So welcome to the Statistical Methods for Health Equity webinar series. This is a monthly webinar series, excuse me, series focusing on statistical and machine learning methods that have the potential to promote health equity. So, for example, methods that can shed light on the complex factors underlying inequalities, or designing fairer algorithms that appropriately take into account the different biases that exist in biomedical data sets. So this is a series co-hosted by a few organizations, the Alan Turing Institute, specifically the Health Equity Interest Group, the UCL Statistical Science Department, which is where I am based, and Data Science for Health Equity, also known as DISHI. So DISHI is a global community of experts and enthusiasts working at the intersection of data science and health inequalities. And DISHI's aim is to ensure that the latest research and innovations in data science, machine learning, and AI improve everyone's health, and especially those in underserved groups. So if this sounds like something that you're interested in and you haven't come across DISHI before, there are a few ways to get involved, and I'll post these in the chat very shortly. Today, it's my great pleasure to welcome Vincent Jeanselme, who's a friend of DISHI and has been involved with the community for a good few years now. So currently, Vincent is a postdoc researcher at the RE-AIM lab at Columbia University, working at the intersection of machine learning, healthcare, and decision making. He was before that a PhD student at the MRC Biostatistics unit at the University of Cambridge. And Vincent is I'm very excited to see that he'll be talking about AI-based risk prediction for improving decision making in healthcare. So without further ado, over to you, Vincent.
Thank you so much for the introduction. So yeah, today we'll be speaking about how can we improve the risk prediction in order to improve decision making in healthcare. So the main motivation of my research is that everything in healthcare is made of decision, from the decision of the patient to seek for care to the decision of the practitioner to actually provide that care, when and whether to provide that care. Oh, so if there is any question during the talk, please feel free to interrupt me. I just saw like some pop-up coming, so yeah, feel free. Um, the potential of AI in this context is if we could predict what would happen following one of those decisions, we could better inform those decisions. For instance, here, if I were able to predict what would happen following the treatment, I would avoid treatment in that context because that would lead to a negative outcome for the patient. However, that comes with a lot of challenges because medical data are the result of imperfect decision. If the decision were perfect in the first place, there would be no need to use AI. And because they are imperfect, learning from this data is quite challenging. For instance, the decision from the patient is not random. Patients that are seeking care are often sicker than patients staying at home. And therefore, we have a distribution shift between the patient that we observe and the model, and the population we would like to apply the model to. Similarly, the decision of a practitioner is again not random. That's not just a flip of a coin. We have practitioners, that make informed judgment to treat the patient that would most benefit from that. And so again, that should lead to a distribution shift between what we observe and what we aim to model, because the patients that are sicker will be more often treated. So that's a few examples of all the statistical biases that emerge from those imperfect decisions. One of the particular interest of my research is how there is some heterogeneity in our population. And so Bria was mentioning that at the start about how those heterogeneities in the population might lead to different decisions. For instance, in the US, it's very common that patients that are publicly insured will not seek care or seek care much later in their condition trajectory. Similarly, the decision of the practitioner might be impacted by those socioeconomic factors. For instance, darker skin, patient would be less treated for skin cancers than whiter skinned patients, because we have a better understanding of the condition for a subgroup that has been more studied throughout its history. And so we really need to account for all those biases when we leverage AI. And so my research really aimed to leverage AI to improve medical decision-making while mitigating all those biases that I just described. Today, we'll be speaking about one particular aspect of machine learning modeling, which is competing risks. That's a specific context in survival analysis that we'll further describe, and how that impacts the risk estimation and algorithmic fairness. So that joint work with both my PhD advisor and now my advisor at Columbia. So the main motivation here is how can AI actually inform treatment? We have a patient going to the practitioners, and now we'll focus on just that step where the practitioners aim to decide if they should receive or not the treatment, if the patient, sorry, should receive or not the treatment. The way we do that currently is by estimating the risk following, sorry, I don't know if you see the bottom of my screen because of the window. Yeah?
It's all fine. We can't, I think we can see it right at the bottom.
Okay, fantastic. So right now, the way we are doing that is by modeling the risk given time. So here you have the x-axis at is time, the y-axis at the probability of observing an event, for instance, a cardiovascular disease. And so you will model the risk given time. And so if that risk, sorry, is above a certain threshold at a certain time horizon, so let's say at 10 years, if you're above 10%, we will treat you. Otherwise, we would just wait and wait until, sorry, the next time, sorry, you see your practitioner. How do we build such risk estimate? That is the target of survival analysis. So we'll collect information about a patient and we'll try to predict the time to the event of interest. So for that, we'll create a study, we'll gather data. In the study, some of the patients that you observed will have the cardiovascular event of interest or the event that you're interested to model. But what often happens, because the study is limited in time, is that you will have some patients for which you will not observe the outcome of interest. Those patients are known as censored. And so here I represent that as door, they exit the study, either because the study ends or just because they left for a reason unrelated to the outcome of interest. What is important here is that those censored patients are still at risk. After the time that we observe censoring, the event can still occur. For instance, the patient lived after 1 year, but 2 years later, we actually observe the cardiovascular event. And so we have this link that I present on the right, where you have this dotted line between exiting the study and actually observing the cardiovascular event, because that still can occur. The third type of patient, and that will be like the main topic of this presentation, is patients that experience a competing risk. So a competing risk is an outcome that precludes the outcome of interest. So here my patient, for instance, the third patient here, dies during the study, and therefore we are no longer at risk of the event of interest, which is cardiovascular event. So here the key difference between the censored patient and the patient who dies, both of them do not observe the outcome of interest, but the patient who we censored is still at risk versus the patient who dies is actually no longer at risk of the cardiovascular event. So here on the right, again, just showing like we have this cross that can't happen. Sorry, this arrow that can't happen between the death state and the cardiovascular event. However, in the literature, 50% of the studies do not account properly for competing risk, treating them in the same way than they treat censoring. So here it's from 2012. This study was looking at medical analysis, but it is very much the case across the literature, both in computer science and machine learning and medicine as well, that we often ignore those competing risks. But there have been a lot of empirical evidence since 1974, so like the first models that actually try to account for those competing risks, that shows that if we ignore competing risk, we would obtain one estimate. Here I present on the right, the one estimate we would obtain ignoring competing risk. And we would obtain a very different estimate if we were accounting for competing risk. So there have been empirical evidence for certain type of models, but we already don't know how bad this impact is. And so my work here is theoretically quantifying this issue. So I quantify the difference between those two curves, ignoring and properly accounting for competing risk. I propose a new methodology using neural networks to better model this type of outcome. And finally, I evidence the impact on practice, because as we have two different risk estimates, the recommendation we would make of treating or not treating the patient might change just because we do the modeling differently. Moreover, when we do the theoretical analysis, what we see from the math that I will describe later is that if two different groups present different risk profile for the competing risk, so here women have a lower risk of mortality than men at the same age because of longer life expectancy, the impact of this bias of the difference between the standard modeling and the proper accounting of competing risk will be different in those two groups. So here women will be less impacted than men would be. So here what I show really is that a very simple assumption we are making at the modeling stage can actually impact differentially different groups in the population just because they present different risk for an outcome of interest. So I will first quantify the error associated with the current practice of ignoring competing risk, then propose a methodology to better model those competing risk, validate this theory through simulation, and finally measure the impact on cardiovascular care management. I'm happy to take already any question if there is any on this introduction. No? Okay, sounds good. So I will quantify the error. So for that, I wanted to first give an intuition a bit about what is survival analysis. So here on the x-axis, you have a predictive variable, let's say age or age or weight or any kind of covariance that you can measure on your patient. And on the y-axis, you have the event time of interest. If that was a simple regression task, you will just fit a curve. So here, let's say this blue curve will be quite a good fit for this data set. And you will be done with this analysis. You will have what is the time of event given my different covariates. You have an estimate given that, and you can therefore estimate the risk of the event at different time horizons. The issue that I was mentioning about censoring is because my study might last only a certain period of time because of funding, again, that will only last a year. And so all the points outside of this box are never observed. We only observe the green dot here in the box. And so if I just fit a curve looking only at the observed outcome, ignoring the censored one, we would have a very different fit than if we were properly accounting for those censored patients. And so that's the main point of survival analysis, is to account properly for those patients for which we did not observe the true outcome, but we still know that they stay in the study until the end of the observation period. The second challenge that I was speaking about is this competing risk. So here, those black dots, are patients who actually died. And so because they died, the event of interest never happens. It's similar that if you were pushing to infinity that event, because it will never happen in the future. And so we are pushing them on the y-axis. And so we'll have a very different fit again from the dotted line here that will represent what will we fit if we were only looking at observed outcome. So that's very much just giving an intuition of why we need to account for both censoring and competing risk, because that's very biased, the estimate of the time to event, if we do not properly account for those outcomes. The way we'll do that is through formalizing through a directed acyclic graph. So here, each node represents a variable. So here, my X will be the covariates we observe on our patient, demographics, lab test, anything that you would have measured on your patient. And then on the right side, what I show here in these orange dots are the different time to events. So here I have only the cardiovascular event and deaths that are my two competing risks, but we can generalize that to any number of competing risks. So we can have many more than just those two. So I will just generalize that to those are kind of competing risks. So that will be all the event time. And in parallel, there is a problem of censoring that I was mentioning, that the patient might leave the study for reasons unrelated to those outcomes of interest. But both this C and TR are not observed. What we actually observe is only the first event. So here, what I represent is this last dot, is this time of event and the type of the event, that is the first event that is observed. So for instance, if my patient dies, we'll have the time of death and the label will be death. If the patient has a cardiovascular event, that will be the time to cardiovascular event, type being cardiovascular event. So that's the kind of data that we have collected. And from that data, what we aim to model when we do the modeling of competing risk is to model this joint quantity. So what is the probability that my event of interest, so here T, subscribed to cardiovascular disease, happens before small t? And then the intersection that I present in the second part of the joint is that all the other events should happen after that event. And so that's the quantity that we aim to model when we do account for competing risk properly. The thing is, when we do the standard modeling that ignore all the competing risk, what we model is actually just the marginal. So here on the left, I show what this FNC non-competing is. That is just the probability of the event of interest happening before time t. And so now we have this kind of formalization of those two quantities. What you can do is computing the difference between those two. And so that's exactly what I'm proposing to measure the bias that comes from this practice of ignoring competing risks. So here I do the difference of NHC and FC, the two quantities I just described, and I normalize it by the maximum of the two values. When you derive it through Bayes' theorem, really it's very simple here, but what we show is that it's directly equal to the probability of not observing the event of interest, given that the event of interest will happen before t. The first thing that is important here is that this quantity is positive. So that means that when you ignore competing risks, so the standard practice that we often do when we model this kind of time to event modeling is that we always overestimate the risk for a patient. So we overestimate the risk of cardiovascular disease for all the patients by just ignoring those competing risks. And so here, what I represent is, again, given time the risk, what would happen under standard modeling, accounting for competing risk. So overestimation means the standard modeling will always be above the competing risk, the proper modeling of competing risk. But further, what I show is that the difference between those two curves is directly proportional to the probability of death. And so it's critically important, particularly in healthcare, where the data that you have often is gathered about very sick patients, where the probability of death is quite high. So in the data set I will describe later, we have close to 20% of the population that will actually die over the study period. And so the bias that we have is quite large. Further, as I was mentioning, now what I can do is computing the difference between the woman group and the men group in our population to look at how the bias will impact those two groups differently. Applying just the previous definition, we just see the difference between the probability of observing the event in the woman group and men group here. And so what that means is that the bias here, again, the standard modeling will be the top line, woman will be the second line, and the third line will be men, because what we have shown, is that the probability of death being smaller for women, the bias coming from standard modeling will be smaller for women. So we would overestimate risk more for men than for women here, just because their probability of the competing risk is different in those two different groups. Okay, just to put in a nutshell what I just theoretically showed. First, I quantify the bias associated with the standard practice that we are currently doing in machine learning very often, and even in statistical analysis of time to event data. I show that this practice leads to always overestimating risk. And finally, I identify how if different groups present different risk for that competing risk, we have a fairness consequences of this practice. We would overestimate risk more for one group than for another. And all of that comes from a very simple assumption we are making at the modeling stage. Here, there is no bias in the data. Even if the data were perfectly observed, we will still have this issue just because of a very simple assumption we are making when we are modeling that data. Okay, so now I will propose a new methodology to model those competing risks. Again, I'm happy to clarify anything on the theory if there is any question, but I don't think I saw any on the chat, so I think I'll just continue. Yeah? All good? Yeah. So again, the modeling that we are interested to do is this joint distribution. That's the same quantity I presented earlier that is known as a cumulative incidence function. So that's the probability of my event happening before a certain time horizon, and that all the other events happen after that time. The way we do that is by maximizing the likelihood. So here I put the log likelihood. We don't need to go too much into the detail of the math, but there is two main parts. The first part aims to account for the observed event. So we maximize the likelihood of observing the event in exactly the time that we observe the event in the data set. While the second part is about censored patient. And here we try to maximize the probability of observing no event. So nothing happened until the last observation for those patients. So that will mean, like, for instance, after 2 years, the study ends, we did not observe anything for those patients. We maximize the probability of not observing any event over those 2 years. The key thing that we need to notice here is that we need both the quantity f, so the joint distribution, and its derivative. So the derivative will be used for the observed events versus the full joint will be used for the censored. And so that's the main challenge, is that we need those two quantities. The way the literature has done that is by modeling the derivative, because it's just need to be positive. That's the only constraint we have over that derivative, and then integrate it to obtain the full joint. Or make very strong assumption to obtain a closed form derivative and integral. So this way you will just obtain the joint for free just because of the closed form integrals that you would obtain. However, when you do integrals, it's very expensive. So when you make, those assumptions on closed form, you're very much constrained the kind of function you can model. And when you make the integral, you're no longer constraining the shape of the function, but what you do is very expensive, because here on the right side, what I show is how you would approximate an integral. So for each vertical line, you will need to compute the value of the function. Here I do a very simple approximation of an integral, but that will require a lot of evaluation. And so if you think of a neural network for modeling those quantity, it's become very expensive, because now you need to go through a neural network multiple times. What I propose to do sounds very simple. We just model the joint and we'll try to derivate, to obtain the derivative. Differentiate, to obtain the derivative. So that's very easy, and that's very theoretically, that's exactly the same, but empirically, it is much more efficient, because all our machine learning libraries are made for differentiation. We have automatic differentiation being the main tools to train neural networks, and therefore all our libraries are optimized for that. Further, it's exact. Automatic differentiation is as exact as a machine can be in order to compute the derivative. So we are not making any assumption anymore, and we are obtaining both quantity exactly. Further, what I show in the paper is how that leads to state-of-the-art performance. We perform as well as the best models that existed so far, but we are 4 times faster, because now we do not need to make those integrations that are very expensive. Okay, so how do we do that? The main challenge now is that we need a neural network or a model that directly models the joint distribution. So here what I propose is decomposing using like the base decomposition. So here on the top part, you will have the conditional, what is the probability that my event, cardiovascular event, happened before T, given that this event will happen before death. That will be the top part of the neural network. And the bottom part will just model the probability of cardiovascular event happening before death. You multiply those two and you obtain the joint that you are interested to model. So I will just focus on the first line to understand what's the challenge here in order to model that quantity. So we have an input X, let's say a covariates that we have measured on our patient. We are going through an embedding neural network, so standard kind of multi-layer perceptron. And now what we aim to model is the probability of the event happening before T. The main challenge here is that this function needs to be what is known as monotonic. That means that the output of that neural network should increase with the increase in the time dimension. So if my risk at 1 year, if in 1 year, I have 1% risk of a cardiovascular event, in 2 years, that can only be bigger than 1%. And so we really need to enforce this monotonicity in the output of the function in order to model that, that particular quantity. The way I do that is by zooming in again in what is a neural network. So let's just remember what's a simple 1-layer neural network. Here, I have a sigmoid function that takes as an input my time dimension multiplied by weight matrix plus a bias. A very easy way of enforcing monotonicity is just by enforcing all the weight in W to be positive. If I multiply an increasing quantity by anything positive, the output of that will always increase. And so we achieve monotonicity just by enforcing all the weight to be positive. So for instance, take all the square in your matrix and you will obtain a monotonic neural network. What is very important is this long paper that I'm mentioning at the bottom of the slide that shows that such neural networks are actually universal approximators of monotonic functions. Why is it important? It is important because that ensures that we can model any function. We do not constrain the type of functions that we can model with this kind of neural network. And that's a very important property, because if we make some approximation or if we constrain the family of function we can model, it's as good as if we were doing a closed form integral assumption where we constrain the family functions. So here, I do not constrain anything by doing that. And so in parallel, as I was mentioning, the second network, the bottom line here is very simple. It's just a multi-layer perceptron with a softmax that ensure that the sum over all the output is equal to 1. Again, when we multiply those two quantities, we obtain the joint. And so when we do a forward pass, what we obtain is this quantity in green that I overlay it on the right. And when through a backward pass through the neural network to do automatic differentiation, we obtain the differential that we are interested to have to compute the likelihood. So now with one forward pass, one backward pass, we can compute the whole likelihood and maximize the likelihood to train that neural network. And so that's a new methodology to train neural networks for survival analysis. The main advantage here is that it's very efficient to do that, and it's exact without any constraint on the type of function. And the advantage of neural networks here is their flexibility. So I give the example that we could use many modalities. For instance, you can use an image directly, an X-ray, for instance, to predict what will be the risk of a cancer recurrence. So directly using the X-ray, we would just need to change the neural network E to be a convolutional neural network or a neural network that will be adapted for the modalities. Similarly, we could consider time series, text, anything that will be relevant in order to predict the outcome of interest. Okay, that's the second part about the neural network. Again, happy to take any questions, but I don't think I saw anything on the chat.
Now, can I ask one or two clarifying questions, please? And I'll
Yes,
just encourage people to post in the chat as well if they have any questions. One is, so the automatic differentiation replaces how are people computing those derivatives before? Was it just on like a closed, like an assumption around like the form of the
either a closed form or what they were doing is actually modeling the derivative using a neural network. So for that, you just needed to ensure with a soft plus at the end of your multi-layer perceptron with a soft plus at the end, and then they were integrating that to obtain the full joint. So they were modeling the derivative and then integrating it.
Okay, I see. And then the other question is around the monotonicity. Do you lose any? I guess this universal approximator is you can universally approximate any monotonic function, right?
Yes.
And then, but do you lose anything in kind of imposing? Because I guess by this kind of weights constraint you have, that's like a more restrictive constraint than it needs to be, right? But do you lose much in using this kind of like more constrained neural network versus something a bit more flexible?
You can use alternative. I think that will just change how fast maybe the neural network will converge. But like from the proof, like they say if you have 3 layers, you can really approximate any function. So that's like one of the interesting property of those neural networks. I think there is people that have proposed some more efficient approach. I haven't tried, but yeah, maybe that will lead to faster even convergence of the network.
Great, thank you.
Thanks. Okay, so I have some simulation. If we're good on time, yeah, we're good on time. So I will show just how we can validate the theoretical result I spoke about before, because now that we are modeling those quantity, we make some approximation or the empirical fitting to our data might be just approximate, and therefore we might be a bit further away from that theoretical result. So I just wanted to check that the theory was making sense and that with the different methodologies that we could use, if we were aligning or not with that theory. So what I will do is generate data using the same directly acyclic graph that I was presenting at the start. We'll model the covariates using Gaussian distributions. And then we'll sample the censoring time and the event times given those covariates using Gompertz distribution. It's like a standard form of survival distribution. And what we actually observed is the first event out of all those different events that are sampled from Gompertz. And so here what I present is on the x-axis, the quantity I was computing at the start, what we would theoretically measure, because we have the perfect control over the simulation, so we can compute the exact quantity here. And on the y-axis, I will compute the difference between a neural fine gray, so the methodology I just presented that consider computing risk, minus the ones that ignore computing risk, normalize that, and therefore obtain the empirical quantity of the bias associated with ignoring computing risk. Each dot here represents one simulation. We have 25 simulation. And so what we want is to be well aligned with the black dotted lines, dashed line, sorry, that represent when the theory perfectly aligned with the experiment. As you notice, the L function, so the loss, is dependent on time. So what you can do is computing at different time. So let's say at 5 years and 10 years, you can measure how well the theory aligned at different time horizons. And so here I present 2 different time horizons, because what we see is that earlier time horizons are harder to model because we have less observed event, and therefore we are further away from the theoretical result. So that's like the first thing, is earlier time horizons are harder to model here. But what I wanted to show here is by comparing different methodologies. So I consider 3 neural networks. Neural fine gray is the one I propose, but they have been deserved. This model was doing ordinary differential equations, so doing the integral parts that I was describing before, and DP that discretize the time horizon in order to approximate. So both of those methodology use neural networks in order to model the survival function. DP makes stronger approximation by discretizing. And finally, the red dots represent the fine gray methods, which is the original one from 1974, that make a very strong assumption of proportionality in order to approximate the survival functions. What we see is that the model that makes the most assumption, the most approximation, DP here, is much further away from the theory. So it seems that when you make too much approximation, you're actually getting further away from the theory. But otherwise, at the longer time horizon, everything very much aligned with the theoretical result, meaning that whatever flexibility you use, you always overestimate your risk proportionality to proportional, to the probability of the competing risk. So often we are tempted to use more advanced neural networks, more advanced machine learning tools in order to model the quantity of interest because we assume the fit will be better. The fit is better, but we just better align with the theoretical results that says that we'll overestimate risk. Similarly, we can compute the gap between men and women error. So exactly the same plot that before, but here on the x-axis and y-axis, I compute the gap that I was presenting earlier. You can do that for all methodology. And again, what is very interesting here is like that the DP strategy and the fine gray are the ones that are furthest away because they have less flexibility in modeling the outcome, and therefore we align less well, with the theoretical quantity. So again, more flexible modeling better aligned with theory, but increasing the flexibility is not enough in order to account for competing risk. So it's critical to account for competing risk to ensure that we do fair and precise modeling of risk. Okay, that was a very short simulation because I want to spend more time on measuring the impact on cardiovascular care management. So everything I've presented so far demonstrates the importance of modeling competing risk, propose new methodology to do that, and validate that. Now we measure the impact on practice. So current preventive treatment recommendation for cardiovascular disease is based on such risk score that I presented before. So you will estimate the risk of cardiovascular disease given time. And if the patient has a risk over 10% to have a cardiovascular event in the next 10 years, we would actually treat those patients with statin in the US. So statin is a drug, a blood-lowering drug. No, blood pressure-lowering drug. Yeah, I'm not sure my English is right there, but that will lower your blood pressure. So we'll give statin in that context to the patients that have a risk over 10% to prevent those conditions to happen. The way we have built that risk is using the Framingham Heart study. So that's a population that in the US that we have collected data over years, 4,000 patients, more than 4,000 patients. We have more than 4,000 patients for which they did not have any cardiovascular event at the start of the study. We collected demographics, laboratory tests, previous conditions. So we know if they are diabetics, we know what their blood pressure at the start, and their age and sex. And we measure that at the first event, at first visit in that study. And we aim to model the cardiovascular disease risk, sorry. In the population we have, 26% of the patient will present a cardiovascular event during the 30 years if I remember correctly, of the study. 56% of the population will be censored, and around 18% of the population will have a cardiovascular, will actually die during the study. So the first thing I really want to attract attention is that the majority of patients actually do not observe the outcome of interest over the study period. So it's critical to account for both censoring and death. What is important is that the original risk score that is still used in some part of the world did not consider death properly. They consider death and censoring in the same way. And so as I've shown so far, that will really much overestimate the risk associated with cardiovascular disease for our population. So here again, I put the same plots since the start. We have the probability of observing of cardiovascular event given time, not accounting for competing risk will result in a larger risk estimate than properly accounting for death. And so that can have a direct impact on the recommendation of treatment because I can be above that threshold if I did not properly account for competing risk, and below if I were actually accounting for competing risk. So there is a risk of over-treating the population. So what I will do here is looking at how modeling competing risk will change this recommendation in our population. So I will focus on all the patients that are over 40, because that's patients that to whom we would recommend statin. In this population, you can estimate that 13% of the population will have a cardiovascular event. You can estimate this percentage by accounting for the censoring process. So here we'll assume 13% will actually have a cardiovascular event in the data set. All the orange patients here, underline patient, are treated under the Framingham risk score. So that's the original risk score that has been proposed. We would treat all those patients. What is important is all the patients on the top are overtreated. We would like to reduce that number because they do not benefit from treatment because they don't observe the outcome of interest. Versus the bottom line actually benefit from that treatment. So we want to keep those patients on the bottom line to be treated while reducing the one on the top. Here, what I represent is if I consider machine learning tools, so a neural fine gray, but that ignored competing risk. We did not properly account for competing risk. We just model death and censoring it the same way. What we see already is that using these more advanced machine learning tools reduce the percentage of patients that are overtreated. So that means that more flexible model better model the risk, and therefore we can avoid overtreating the population. But the number of patients that are actually impacted by the censoring versus the competing risk versus non-competing risk modeling are only those two patients. So here, what I do in blue is underlying the patients that will be treated under the properly under the models that properly account for competing risk. So in the box, we have the patients that will be treated under models that ignore competing risk and not treated if we were properly counting for competing risk. That represents only 2 patients out of 100. So I really wanted to emphasize what that represents in the US alone. Given the Census Bureau, there is 165 million patients older than 40 in the US. And the cost for a statin is around $400 per patient per year for generic drugs. So that's like a lower estimate of that cost. And so that represents a 1.2 billion a year of savings if we just avoid overtreating those 2 patients. So it's quite important. Like this impact of a very simple assumption we are making at the modeling stage can really have a very big impact on the recommendation we are giving at the population level for treatment. And if I compare to the current practice, so when we do a less flexible modeling that ignore competing risk, this cost is even 3.5 billion. There is even a larger savings we could have by actually doing a proper modeling and more flexible modeling of the outcome. I don't know if there is a question. I think I heard some. No?
Yeah, there was a question from Chris Hart saying, is there an assumption here that the death events, as you define, are completely independent of the cardiovascular events? Like if you factor in cause of death, where death might be due to cardiovascular disease?
So when I speak about the competing risk, that will be only death from other causes. Death with a cardiovascular event will be considered as a cardiovascular event. But there is still an assumption of independence given the covariates. So in the DAG I was representing, everything is independent given the covariates. Okay, thanks. So as I was mentioning, the risk is not only that we will overestimate the population, but because our population is diverse, so here I will split between men and women, what we can do is the same analysis of looking at who will be treated under the current practice. So here again, in orange, all patients that will be treated under the Framingham risk score. And in blue, the ones that will be treated under the proper modeling of competing risk with a more flexible neural network. Sorry. What is important here is that the number of overtreated patients, the number in orange here that will not be treated under the more flexible neural network is larger for men than for women. So that's very much aligned with the theoretical results that say that the bias in the risk estimate will be larger for men than for women because women have a lower chance of death than men. So we expect that this model will more benefit men than women. But what that means is under a fixed budget, this corresponds to redistribute treatment from men to women because now we more equally distribute the treatment over the two populations. So very simple assumption, again, that we made at the modeling stage really much could impact the recommendation we are giving to our patient and therefore access to treatment. So treating competing risk as censoring really hurts the accuracy, but also the fairness of our risk estimate, potentially leading to overtreatment, but also harm. Right now, I was speaking about statin. There is not too much side effect to statin. But if we think now about chemotherapy and the recommendation of chemotherapy, it will often be based on the risk of recurrence or risk of negative outcome. And the cost of chemotherapy is not only money, but also very much quality of life for the patient. And so there is a real harm associated with overestimating risk. Finally, I just wanted to mention that this common practice has repercussions beyond healthcare. Whenever we aim to estimate risk score, we have a similar issue. If we have competing risks, we really need to account for those competing risks in order to have an accurate estimate of that risk. So here I just give the example of a client going to the bank asking for a loan. We would estimate that risk, that client's risk of not repaying their loan. So the risk of defaulting on their loan. If that risk is above a certain threshold that the bank is okay to take for that patient, that client, sorry, we will not give the loan. Otherwise, we'll lend the money. In that context, we'll still have the problem of censoring because the data we'll have collected, some of the client would not have fully repaid, but not defaulted either. And there is very importantly the problem of competing risk for clients that would actually have fully repaid before the end of the study. And therefore, there is this risk of overestimating the risk of defaulting and not lending money to clients that would actually not have that much risk. And that actually all for me. I'm very happy to take any question if there is any.
Amazing. Thank you, Vincent, for a wonderful talk and like amazing visualizations and graphs. I love how you present the impacts of the different modeling on the little people. You're getting loads of applause, I can see. So there is, for the time being, one question in the chat that I'll read out. If people would prefer to just ask their question out loud, just stick a hand up on the Zoom, and we can manage it this way. So actually, Alexander has a couple of questions. I'll read the first one out first, which is there any way to quantify the uncertainty in the prediction estimates for the time to event as a result of the limited sample size, or would you have to resort to something like bootstrapping?
That's a good question. I haven't looked too much in neural networks literature for uncertainty estimation. I would bootstrap. I'm sure that we could do, maybe more advanced estimate of uncertainty. I'm less familiar with that.
Yeah, I think that bootstrapping, I think it seems to be like one of the main ways with neural nets, where you can use these like weird dropout type ways where you kind of like hold different nodes fixed and then do some sort of like randomized retraining. I don't really know much about this, but I know this is something that people love doing in the neural net literature. And the second question was, is there any assessment of the risk of underprescribing as a result of the NFG risk score versus Framingham?
Yeah, no, that's a great question. Actually, there is a real risk. And so there is always the necessity, once we have developed a risk score, to do this cost-benefit analysis. Because here, there is a 0.2% of population that will not be treated under the more advanced neural network that would benefit from the treatment. And so that depends on the cost you will put on, not treating a patient that will need the treatment versus over treating the population. And so that's definitely a step that is necessary in order to select the threshold. Here, I selected the threshold at 10% using the current practice and care, but definitely that will change that will potentially, change that threshold, and therefore the impact of avoiding treatment for patients that will require treatment might change for sure.
Mm.
Sorry, I'm not sure if I was very clear, but the jet lag is making me bug.
No, I think
that answers the question very well. Thank you very much.
Okay, fantastic.
I have a couple of questions. One is that you allow for like the censoring distributions to vary with the covariates, right? Because you're looking at different competing risk distributions by your kind of like sensitive characteristic, and is that also true for the censoring distribution as a default?
Yes, because I try to maximize the probability of not observing any event given the covariate as well.
Yeah, okay, cool. Here's a question from Begonia, which is, what if you have a multimodal data set with images and clinical covariates? Have you tested your methodology in this setting? Like, does it require any kind of specific architecture changes? Yeah, that's a very interesting question.
Absolutely. So it's easy to train if I have one image and one outcome. The only thing that will change is the embedding layer I was mentioning in my neural network architecture. So I will just use a CNN or any neural network that will be better adapted for an image, for instance, and train my model jointly. So I will have my CNN, then the monotonic neural network to model the outcome of interest. And we can train that as you usually training your convolutional neural network. The problem of multimodality, it's always challenging of how do you weight the different modalities. You can just concatenate maybe the different embeddings. So you will have a CNN to embed the image, potentially the covariates in parallel. You concatenate those two and then go through the same monotonic neural network. So that will be a possibility in order to use multimodal data set. But yeah, I think there is challenges with multimodalities when, for instance, there is only one modality observed. All of that will create additional challenges for sure.
Thank you. I've got one more question. If anyone else has any further questions, do feel free to post them in the chat. My question is, I guess it's a more like high level one, which is, this is like clear public health consequences, and is there an ambition to like try and get public health officials on board in the US to try and change the policy for how statins are prescribed? Like, have you had any experience like speaking to clinicians or public health officials about these kinds of problems, and how on board are they with changing these kind of like policies, which are kind of have been in place for a few years now, right? Like it's
Yeah, no,
crazy.
absolutely. I would love to, if you know anyone, I would love to speak with public health. Like definitely, I think it's an important problem, and there is across applications. That's not only like for cardiovascular disease, the same for cancer recommendation, cancer treatment, recommendations. A lot of conditions are based on this kind of risk score. Same thing when is the next time you will go for a checkup, like for a screening, that will be based on such risk estimate. And therefore, anytime there is a competing risk, we might overestimate the risk of our population. And so, yeah, definitely, I think that's an important problem. What I wanted to mention is actually in the UK, they did a change on the new cure risk. They consider a competing risk model compared to before they did not. So what I would be very interested is actually see how this change of model actually change the way we recommended treatment across the population and see if we observe such change of, like, for instance, women and men having a more equal treatment after the integration of that model. So that would be something I would be very interested.
Yeah,
look.
interesting. Do you know what they use to model the competing risks? And presumably it would have been like a parametric thing, right? That
or fine and gray, like, yeah, more standard kind of statistical tools, not neural networks for sure.
A question from Chris. Is there a risk that this extension to modeling risk could introduce socioeconomic biases if applied to multiple different types of risk decision? And then if the net effect is to reduce treatment and this was applied to multiple treatment decision models, e.g. Cardiovascular disease, diabetes, and others, you could see a risk of a subset of individuals not receiving treatment because of a higher risk of mortality, which may be outweighed in each case with a one versus all competing risk analysis. Yeah, wonderful question.
I love that question. Yeah, it's definitely a big issue. So I think it's critical to account for competing risk when there is a biological reason for having a difference in the outcome. But when it's coming from socioeconomic factors, so for instance, different demographics in the US will have different mortality rate, and it's not linked at all to any kind of condition, then there is a risk of reinforcing those disparities. Just because I'm moving off country where there is a higher likelihood of mortality shouldn't change my recommendation of using a treatment. And I think that that's definitely an issue, but I think it's a broader issue in the fairness literature as well. How do we disentangle the socioeconomic factors from potentially biology differences that we have in different groups of the population? I think, yeah, it's a great question. I don't know how to do that properly, but definitely that's a risk if we model those competing risks that would come from socioeconomic factors and not biological differences.
Yeah, totally agree. The disentangling of the biology from everything else is such a big challenge, and I guess there's a hope that genomics and kind of widespread genomic sequencing will help to disentangle those things, but that's a very long time away. Awesome. Thank you, Vincent, for an amazing talk. I'm going to post a few things in the chat for some upcoming Dishy activities. So in particular, our next statistical methods webinar is taking place in December, on the 8th of December. So I think 4 weeks yesterday, where another friend of Dishy, Claire Coffey from University of Cambridge, will be presenting some recent work, not dissimilar to this, also in fairness in clinical prediction modeling. So if you enjoyed Vincent's talk, then you should enjoy Claire's as well. A couple of things that have come out of the theme over the last couple of weeks. We've been doing a blog series, so I've linked a couple of fantastic blogs in the chat there. And then a survey that we have just released in partnership with Cancer Research UK on the challenges in embedding inclusion and diversity in data-driven health research. So it should only take about less than 10 minutes of your time, but if you're involved with or influence study design in biomedical research, then we would love to hear from you from that. And so, yeah, as I said, it shouldn't take much time at all. So thank you again, Vincent. Thank you everyone for coming, and yeah, Vincent, get some sleep.
Thank you so much for having me.
Thanks for such a great talk. Cheers.
Thanks.
Bye everyone.
Bye-bye.